So you are welcome back. We now want to look at the various probability distributions that we have. We will look at two of them, three of the discrete and then one continuous. But before that, let's try to understand what random variables are. So we say that a random variable is a variable whose value is subject to variations due to randomness. Okay. So we have discrete random variables and then continuous random variables. A discrete random variable is a random variable whose value is subject to a specified set of exact countable values. So such a variable assumes only exact countable values like 1, 2, 3. And for example, integers. And then a continuous random variable is a variable whose value is subject to numerical values within a specified interval or a collection of intervals. So for a continuous random variable, it can take values such as 1.5 because 1.5 is a number between 1 and 2. Or it can take a value such as 2.73 because it's a value between 2 and 3. So for continuous random variables, they can assume values between two integer values, okay, or between two specific values. So let's look at some examples of random variables. The roll of a fair die. We consider this as a discrete random variable because there is an element of randomness. For example, if X represents the outcome, if, for example, X represents the outcome from the experiment of rolling a die, then we say that X can take values 1, 2, 3, 4, 5, or 6. So X is random. It's a discrete random variable because it can assume different numbers, okay? If a number, for example, is selected from the range, say 0 to 100, such as 11.2, 42, 56.63, then that number, or the variable representing this number is a continuous random variable. So usually we use the capital letters X or Y to denote a random variable. Now, we call something a realization. So once a random variable assumes a number, then we say that number is the realization of that random variable. So if I have X representing the outcome from rolling a fair die once I roll the die and I get a 5, and now X is equal to 5. 5 is the realization of that random variable. So another example is let Y denote the number of tails obtained from tossing 2 coins. So first of all, realize that if you toss 2 coins, you can obtain either 0, no tail. If we refer to 2 coins, okay? If you toss 2 coins together, you may get no tail, or you may get 1 tail, or you may get 2 tails, okay? Now, we will obtain 2 tails. I think there's some error in here in this example, but let's focus here. We will obtain 2 tails with a probability of 1/4 because if you obtain 2 tails, the probability of obtaining 1 tail from a coin is 1/2 because for a coin you have just head and tail, and then the probability of obtaining another tail from another coin is 1/2. So 1/2 times 1/2 will give you 1/4. That's how come we have this here. But the probability of obtaining 1 tail is either you will obtain a tail in the first one and a head in the second, or you obtain a head in the first and a tail in the second. So if you write out their probabilities and then sum them up, you are still going to get 1/2. That's how come the probability of getting 1 tail is 1/2. And the probability of getting no tail, okay, is the same as getting 2 heads. If you get 2 heads, it means that you didn't get any tail. So the probability of getting 1 head, for example, is 1/2, and then on 1 coin, and then the probability of getting another head on the other coin is 1/2. So the red end comes to play. So we do multiplication, and half times half is 1/4. So this is why we have, this is the, in summary, this is the probability distribution of the experiment or the random variable representing the outcomes of tossing 2 coins. Okay. Now let's move on to, so if you look at this, when we talk about probability distribution, all we are saying is the outcomes with their respective probabilities. The outcome with its respective probability together form the probability distribution of any random variable. Now let's look at the Bernoulli distribution. So this is our first discrete probability distribution we want to look at. Okay. The Bernoulli distribution is a discrete distribution that has only 2 possible outcomes. So we normally call the outcome 1 as a success, having the probability of P, and the outcome of 0 as the failure, with probability of kill equals 1 minus P. So if X is the Bernoulli random variable, then it's equal to 1 with probability P and 0 with probability kill, which is equal to 1 minus P. Now the mean of a Bernoulli distribution or a Bernoulli random variable is P, and the variance is P kill, okay, or P times kill. Now let's look at an example. A fair die is tossed. Okay, 1 fair die is tossed. X is a random variable that equals 1 if the first toss is 5 or 6, and equals 0 if the first toss is 1, 2, 3, or 4. So you represent X as 1 if you, when you toss, you get 5 or you get 6. And you represent X as 0 if you toss and you get 1, 2, 3, or 4. So find the expectation of X and then find the variance of X. Looking at this question, you can deduce that this is a Bernoulli distribution because X is assuming only 2 outcomes, either 1 for when you get a 5 or 6, or it's a 0 when you get 1, 2, 3, or 4. So the probability that X is equal to 1 is 2/6 because the probability of getting a 2, a 5 when you toss a coin is 1/6, and getting a 6 is also 1/6. But the word here is or 5 or 6, so we add. So 1/6 plus 1/6 gives us 2/6. Simplify to get 1/3. Now the probability of X being equal to 0 is when you get either 1, 2, 3, or 4 when you toss the coin. So 1, 2, 3, 4. Each of them have the probability of 1/6. When you add them, you get 4/6. Simplify to 2/3. So in this case, we are saying that X is a Bernoulli random variable such that X is equal to 1 with probability P equals 1/3 and 0 with probability kill equals 2/3. So how then do we find the expectation of X and the variance of X? We are given the formula here. So the expectation of X is equal to P, which is 1/3, and then the variance of X is P kill, that's 1/3 times 2/3, giving us 2/9. Now, let's move on to a binomial distribution, our second discrete distribution. Now, a binomial distribution is a discrete distribution for a number of successes in a sequence of n independent Bernoulli trials. So if you perform more than 1 Bernoulli trials together, it gives you a binomial distribution. So we consider n as the number of trials. So in the case of rolling a fair die, this time around, we are thinking of rolling the fair die more than once. So maybe you roll a fair die 3 times. Once it is that way, better you toss. Let's look at the tossing of coin example. That's much easier. So tossing a fair coin 3 times. For each trial, for each toss, the likelihood outcomes are either head or tail. So if you toss it 3 times, then now you are saying that you n is equal to 3. That's the number of trials is 3. All right. And for each trial, you are getting either a success or a failure. Based on your definition, head may be success, tail may be failure, or tail may be success, head may be failure, based on your definition and how the question is framed. So in a binomial distribution, the number of trials involved is fixed. Okay, and then each trial is independent of the other. So if I perform one trial, the outcome I get in no way influences my second trial's outcome. And then the probability of P or success is constant for all trials. So if it's the experiment of tossing a coin, the probability of getting a head when I toss that coin is 1/2. If I do that trial again, the probability of getting a head is still 1/2. Now, the sum of the probabilities of success and failure is always equal to 1. Okay. Now, this gives us the probability mass function of x. The probability that x being equal to x is equal to n x. All right, this is the binomial, or the n, choose x. Then p to the power x, 1 minus p to the power n minus x, for x equals 0, 1, 2, up to n. Because if you are looking at the number of heads obtained when I toss a fair coin 3 times, you may get no head. So definitely the number of heads obtained should start from 0. And the maximum number of heads you can get is the maximum number of trials you perform. So if I'm tossing a fair coin 3 times, I can't get 4 heads because I'm tossing it just 3 times. So please take note of the limits of the possible number of heads you can get, or number of successes you can get. And then for a binomial distribution, the expectation of x is np, and then the variance of x is npq. Okay. So as an example, a newly married couple plans to have 5 children. A medical scientist tells them that based on historical family data, they have an 80% chance of having a baby boy on any particular birth. The couple would like to have 3 boys and 2 girls. What probability distribution is applicable to the situation described above? What do you think? This is a binomial distribution because the couple wants to have 5 children. For each birth they go through, they'll either get a boy or a girl. Okay? And then they're saying that the medical scientist tells them that based on their family history, they have an 80% chance of having a boy on any particular birth. So the probability of success, or the probability of having a boy, is constant, is fixed for every single birth attempt they make. Now, this is the couple's desire. They want to have 3 boys and 2 girls. So the B is find the probability of occurrence of the event. That is, the event is that they wanting 3 boys and 2 girls. So the solution for the 3 boys, our interest x assumes our success here will be getting a boy when you go through the after childbirth. Okay. So the probability that x is equal to 3, where n is 5, p is 0.8, of course, because the chance of having a boy is 80% and q is 0.2 and x equal to 3. So the probability that they will get 3 boys is, we fix all these variables, the outcome, the realization of these variables into the formula for the binomial distribution, and then with your calculators you can get this. Now for the 2 girls, in this case, our x now represents the outcome of getting a girl. So the success for us is getting a girl. Okay. So our p now is going to be 0.2, and then q is 0.8, and x equals to 2, n is 5. So once you want to find the probability that x equals to 2 is this, you just fix everything inside your formula and then you get your value. So after doing it for each of the 3 boys and 2 girls combined, the probability of getting 3 boys and, take note, and 2 girls, we have the outcome, the answer you got for the 3 boys, 0.2048, times the what you got for the 2 girls, 0.2048, and that gives you a total of 0.04. Remember, and is multiplication or is addition. So here's another example you can try. The next one the last discrete distribution we want to look at is the Poisson distribution. Now, the Poisson distribution is a discrete distribution used to model the occurrence of an event during a fixed interval where the occurrences is in disjoint intervals are independent. So the interval is usually time, but it can be other quantities. So possible ways of applying the Poisson distribution includes the following. So here we have examples: a Poisson random variable, an event, and then the interval involved. So number of emails received in a day. This represents a Poisson random variable because their intervals are regular, okay, and they're disjoint. No day intersects with another day. So the event is what? Receiving of email, and the interval involved is time. Another example is number of car accidents in Accra in a week. So car accidents in Accra is the event, and then the interval involved also again is time. Then a number of holes along a 1-yard rubber tube. The event is what? A hole, and the interval involved is length. Okay. So in Poisson distribution, we are just saying what is the count? What is the count of events within this interval? And with the intervals involved are fixed intervals. They are the same intervals involved and they are disjoint. So if it's days you are looking at, they are working with days. If you're working in weeks, it's always going to be in weeks, okay? So we represent the Poisson random variable as such, where lambda this is a Greek word called, Greek letter mentioned as lambda. Lambda is the mean of x. Now the probability that x is equal to this function, e to the power minus lambda, lambda to the power x, all over x factorial, where x equals 0, 1, 2, and infinity. It's 0 because in a particular interval, you may get no counts, okay? So if you look at this one, number of emails received in a day, in a particular day, there may be no emails received, but it expands to infinity because you can't tell how many. Maybe you receive so many more. We cannot, it's infinity. You can receive as many emails as possible in a day. Okay. So the expectation of x, the one unique thing about Poisson distribution is that the expectation and then the variance of x are the same. Each of them is equal to lambda. Okay. Now, one other important feature you need to consider here is that the sum of independent Poisson random variables is also Poisson. So if x is Poisson with mean lambda 1 and y is Poisson with mean lambda 2, then x plus y, as representing a new random variable, is also Poisson with mean lambda 1 plus lambda 2. You can extend this property to more than two random variables, more than two Poisson random variables. So as an example, if there are 200 typographical errors randomly distributed, if there are 200 typographical errors randomly distributed in a 500-page manuscript, find the probability that a given page contains 3 errors. If there are 200 typographical errors randomly distributed in a 500-page manuscript, find the probability that a given page contains 3 errors. In this example, first of all, you need to find your lambda, which is your mean, okay? So if there are 200 errors on a 500-page manuscript, then on the average, there will be 200 out of 500 error per page, okay? That is 0.4 error per page. So our lambda is equal to 0.4. Now you want the probability that a given page contains 3 errors. So the probability that x is equal to 3 is equal to, we have a lambda and then we have x is 3. So we just fix everything inside our formula for Poisson distribution, and then with our calculators, we can get this value. Okay. Here is another example you can give a try as you watch these videos and study your notes. Okay, so see you in the last session where we'll discuss the normal distribution.